Simulators are an important tool for validating and debugging the output of AI planning methods. However, current simulators for AI planning use highly abstract environments, which complicates their use for real-world applications. On the other hand, there are state-of-the-art game engines which enable visually realistic environments, but they do not have an interface to AI planning. To help bridge this gap, we present the REAP framework, a real-world environment for aerial AI planning. It uses real-world data to construct a visually realistic environment, while still providing an accurate physics simulation. Our framework is highly modular and uses only open source components, making it easy to replicate and extend. In addition, it is compatible with hardware, so it can be used in real-world applications. The rest of the video is organized as follows. First, I will present an overview of the system architecture, and then we will demonstrate our system live in action. As you can see, our framework is divided into two subsystems: AI planning on the right side and validation and visualization on the left side. We use PlanSys2 with the UPF for ROS2 plugin to generate plans and translate them into ROS2 messages. The UPF for ROS2 plugin enables plan generation with the Unified Planning Framework, providing us a convenient access to many state-of-the-art planning engines. The generated plan is then sent to a ROS2 node, which we call the Action Client. This node handles communication with the planning and visualization subsystem. On the validation and visualization side, we use Unreal Engine 4 with the Asim plugin to create realistic-looking 3D scenes and simulate UAV flight dynamics. Our simulated UAV is directly controlled by a flight control software such as Pix4, which can also be used to control microcontrollers on board of a real UAV. Via a middleware, the flight controller communicates with a component which we call the action server. The action server receives symbolic actions from the planning side and translates them to continuous control commands for the flight controller. So the action server on the left and the action client on the right side handle bidirectional communication between both subsystems. The action client loops through the actions of the generated plan and sends them over to the action server, which then handles the execution on the simulation side. When the simulated action is finished, a message is sent back to the action client, and the cycle continues until the plan is fully executed. On top of that, we use real-world georeference data to construct the 3D environment in which the UAV navigates. This is achieved by importing LiDAR files into the Unreal Engine. Furthermore, we use shapefiles to automatically generate the planning problem. Shapefiles contain georeferenced polygons, which in our case describe the land use of an area. Thus, for example, flight missions can be generated in which the UAV, let's say, visits all forests in an area. Or the altitude of the UAV can be adapted according to the area the UAV is flying in. Lastly, I would like to talk about ways to externally interact with the simulation environment. We use the Remote Control API for the Unreal Engine, which can be used to spawn or control objects in the Unreal Engine. Furthermore, Asim API can be used to control the physics simulation and simulate weather conditions like wind or rain. These APIs can be used to test how the drone reacts to unforeseen events and to further increase the realism of our simulation. Also, a ground control software can be connected to the flight controller to visualize the current flight plan or to override the currently executed plan with custom commands. So that was a brief overview of our system architecture, and now let's take a look at how the system works live in action.
For the first part of the live demo, we show you how the REAP system looks in action. Right now, the drone is at its home position and will execute the commands it receives from the plan executor node step by step. After a takeoff command and sending feedback about the successful action, it next receives a move command with the GPS position of its first waypoint. We accelerated the video here so you don't have to wait for its arrival. After arriving at the first waypoint, it again communicates its success to the plan executor and receives a move command with the coordinates of the next waypoint. This goes on until it finally receives a return to home command after the third waypoint. For demonstration purposes, we defined just a simple goal of visiting certain areas before returning home, but you can get as sophisticated as you would like. It is important to note that we didn't manually define the GPS coordinates of the waypoints, but automatically generated the PDDL problem file from geodata. The environment was also imported from LiDAR. On the top left, you can see that after returning to home, the drone starts to land. Directly above, there is a collision counter which shows the number of object collisions since the start of the simulation. This can help you to determine if the plan got executed properly. Next, we show you how the environment can be manipulated to observe the effect of unforeseen events. Here we start a script targeting the AirSim API in order to create heavy wind for 5 seconds. It is also possible to dynamically spawn objects via a remote control API for the Unreal Engine itself. In addition, you can manually monitor and manipulate the drone during execution of a plan with ground control software like QGroundControl. In the window on the bottom right, it shows the current position based on GPS coordinates communicated from the flight control software, in our case Pix4. It indicates that the drone is currently in off-board control mode, but we can manually override this to stop the drone at its current position. From there, it is possible to return to off-board control mode again, depending on some predefined condition. For the final part of the demo, we show in detail how the modules interact with each other. Here you can see that the simulation has already been started, but is still waiting for a connection from the flight controller software. The reason for this is that so far no other part of the system is running. When we now start the Pix4 autopilot, you can see that the simulation connects to it via Internet Protocol. In the terminal window, it shows the communication protocol as Mufflink that is transmitted over UDP. Next, we start the RTPS agent as the bridge between Pix4 and the ROS2 action server node for off-board control. You can see that message transport between the agent and Pix4 has been established, and the available topics a ROS2 node can subscribe or publish to. As soon as we start the off-board control node, we can see that it is ready to execute commands it receives from an action client. Going back to the RTPS agent, we see which topics were subscribed: battery status, vehicle global position for live GPS position updates, and a time sync. In addition, there are topics it publishes to: trajectory setpoint for setting a waypoint, off-board control mode for allowing autonomous drone control, and vehicle command for takeoff, landing, and actually flying to a set waypoint. The only thing missing now are the planning module and the action client node. For this, we first start the UPF for ROS planning node, so the action client can transmit the PDDL domain and problem files and receive a plan in return. As the final step, we start our action client that, after receiving the plan from the planning module, sends it one step at a time to the action server. The off-board control action server executes the command and sends the result back after finishing it. You can see that the first command after planning is the takeoff command, which gets registered at the Pix4 flight controller through the action server. After the takeoff finished, the action server returns success as a result, so the next step of the plan can be executed. Now the drone flies from waypoint to waypoint in a similar manner, before returning home and landing, upon which the plan execution is completed.
This concludes our short presentation. We hope you found this useful, and thanks for your attention.